review items based on questions, and then I'm going to review a little bit what we talked about last time with the 3-star fix, and then we'll talk about the planets and the moon, okay? So the first one, I just want to do this review about the little d numbers, because we're going to get a new corrective factor today, the v number, which you've asked about in the past. So for the d numbers, the d number happens twice, once in the nautical almanac, once in the 249 tables. So if you open it to any page in the almanac, let's say today, September 11th, you'll notice at the bottom of the column for the sun, for declination, it will give a little d number. It doesn't tell you if it's negative or positive, but all you have to do is look down the row and see, is it increasing or decreasing? Or ask yourself, is it fall before the equinox? Is the sun headed towards the equator or not? And it is, so that means its latitude is decreasing. So that little d number, that's the number it's decreasing by every hour. And the reason that's important is because when we take our sunshot, seldom do we do it right on the hour. It's usually got some minutes and seconds left over. So we have to correct the declination for the amount it's decreased in that time which is elapsed between the even hour and the minutes and seconds which transpired between that time and when we actually took the site. So you write that number down when you write down your GHA and write down your declination, and then for the minutes and seconds, you've got corrections to both, and you go to the tables in the back, the increments and corrections, what we've been calling the minutes and seconds page, and you go to the particular minute, and then the number of seconds. So that's your correction for GHA, and it's always added. To the right of that, in that minute column, there's it says V or D correction. V or D correction, and that's where you apply the D. So the D will give you the correction for the percentage of hour that's elapsed between the whole hour and when you shot it. Okay, so that's the first little D. It's applied to declination. Now, after winter, the sun starts moving in our direction. That's still going to be a negative number until it crosses the equator, and then it becomes positive again as it gains. Well, it'll get positive as soon as it crosses the equator and headed south. So it'll be increasing its southerly declination, then it will reach the winter solstice, start heading back towards the equator. It'll be decreasing like it is now until it hits the equator, crosses it, and then start increasing again. And so it goes. Okay, that's the first one that goes. The second D correction has a similar function. It's there to allow for the increment of something from one thing to another. And that comes in the 249 tables. So for instance, if you go to the latitude 33 page where we've been inhabiting for quite a while, for any LHA, okay, that runs down either side, first of all, you go to the latitude that we're at, the assumed latitude. Then you go to the range that we're at. Is it 0 to 14 or is it 15 to 29? And then you see, well, is the declination in the same name as us or contrary? Well, the sun is in the northern hemisphere, so are we, so it's the same name. It's only going to be that way, though, for a few more days, and then it's going to be contrary. It's going to hit the equator and go in the other hemisphere. But at the moment, we're in the same name, declination 0 to 14. Okay, what you're looking at, there's 3 numbers you're trying to draw from the little particular cell that crosses the LHA with the whole number of declination. Okay, and those 3 numbers are the HC, which is what the sextant would have read at the assumed position, the Z, which is the direction of the sun from that assumed position, and finally another little d. And what that little d does, that makes up for the fact that declinations don't come in whole numbers either. They're always some portion of it. So if the declination is 4 degrees 37 minutes, okay, it's not just the declination, it's not just the HC for 4 degrees even, you've got that extra 37 minutes to allow for. And what that little d tells you then is for each jump of degree in declination, how much is the HC going up or going down? So if you just look at the columns, And note that as you jump each at the same LHA, each jump to the right of a column sees the HC change by the amount of that D. It's an interpolative factor. How you interpolate that? Well, it's at the very back of the 249 table, table 5, and you cross-index that second D number with the leftover minutes of declination. Doesn't matter which one you use along the top and which one along the side, but where those two numbers cross, that's the corrective factor that you apply to the HC. And it will be the getting bigger or smaller, but in this instance, they give you a little bit more hint because those numbers sometimes have negative signs or plus signs. Okay? The reason I bring this up is it was a question, it was a good question, but we also are going to have another factor to deal with called a V number. Some of you have noticed in the almanac, it says V or D correction. Well, what does V mean? Well, we're going to find that out, okay? In a little bit. V or D correction. If you look at the almanac,
victory or delta.
Right, victory or delta. Right, and we haven't dealt with the victory one yet, but we're going to do that tonight. Okay? Okay, so that's, any questions about that, about how we deal with those incremental corrective factors? Okay, the second thing I want to bring up is I want to go back to what we talked about last time using the 249 volume 1. Now, most of you don't have that book. That's okay because I gave you the book for 33 degrees north, the page for 33 degrees north. And the purpose for this particular book is it's to make the process of finding a 3-star fix a lot easier. You can, the process is all the same. It's the same for a star as it is for the sun, really. You still got your sextant number. You still got your height of eye above the horizon. That hasn't changed. And you have a main correction. The only difference is that the main correction, which you apply to your sextant, it doesn't have to factor in for a semi-diameter of the star, so it's always going to be negative. So if you open your nautical almanac to that kind of first page, which is altitude correction tables, you've been taking the numbers for the sun from the first column, stars and planets is in the second column. And just like you did for the sun, you're going to bracket your actual HS between the two numbers there, which gives you the correction. And as you see, they're all negative. So in this case, the dip correction and the main correction they're both negative. That's true for the stars, true also for the planets. And unlike the sun, you don't have to worry about what season it's in. That's for the stars and planet, doesn't matter what season it's in, nor of course are you dealing with an upper or lower limb. Stars and planets don't have a diameter you can see, so it's just there, that's all it is. So that's one difference. The other thing is that if you go to any given page, like you go to, let's go to today, which is the 11th, say, of September, in the almanac, you've been using the sun page thus far, and it's got its own column called sun. But that's in the right page for any given set of 3 days. The left page, if you notice, has several columns. Aries, which is the arbitrary point in the sky that all stars relate from, then the planets, Venus, Mars, Jupiter, and Saturn. So what are those numbers there that you see next to the planet, where Venus is it's tiny numbers here, but Venus is minus 3.9, Mars is plus 0.6, Jupiter is minus 2.3, Saturn is plus 0.6. That's the illumination, that's the magnitude of the planet. If it were a star, that's how bright it would be. So the first magnitude stars are brighter than second magnitude, and so on. So the brightest star in the sky is Sirius, which is seriously bright, but even that is not nearly as bright as, say, Venus or Jupiter would be at the moment. Okay? So it gives you an idea if you're looking at something that's really bright, how relatively bright it is. How do you know what planet you're looking at? Well, there's a couple ways. One, they're not up all the time, but you can go to that graph that I showed you last time in the book, and it will tell you, where the planet is relative to the sun, and it will also tell you if the planet happens to be, in the month you're in, the date you're in, if the planet happens to be too close to the sun to be able to see, which is true for all of them sometimes. But you can also simply just look at the planet and find out what its Zn is, and sort of work it backwards through there if you want it. But the planets are pretty straightforward in that regard. What you'll see though is that you have at the bottom of each planet column not only a D number, which you use the same way, but you have a V number. Now what is that V number? Well, on the three-day page we have here, it's minus 0.3. Well, the V number is what you apply. Is what you apply to the GHA of the star. So, for instance, you start off with Aries, okay? Or let's stick with planets for a second. I jumped from planets to star. My apology. Look at the planet at the bottom of each planet when you'll see a V number. So let's go with Venus. We'll say Venus is minus 0.3. So with Venus, you pick the day and the hour just like you do for the sun, and you're going to have some leftover minutes and seconds. And in addition to writing down the D number, which is going to show you the change of declination of Venus each hour that goes by, you're going to write down the V number. And that V number accounts for irregularities, but because of the fact that the planet is so close, that in addition to the minutes and seconds correction, you've got this thing to deal with. So what you do after you write down the GHA and the declination of the planet, you then write down the V number and the D number, and you go back once again to the increments and corrections page. So let's say we go to, 8 minutes. Okay, and it will tell you for the sun and the planets, for the number of minutes and seconds, what the GHA is going to be, and that number is always additive. So you add that to the GHA you got from the previous page in the almanac. Then you look over to where it says V or D correction, and then you either add or subtract the corrective value for that number, okay? And that adds or subtracts from the GHA of the planet. And then finally, you apply the same D correction that you did for that, as you would have for the sun, and that gives you the declination, okay? Other than that, the planet is just like shooting a star, okay? Now, if I'm gonna put the moon aside for a second because it's its own weird case, and I'm gonna jump from the planets to the stars, and the stars are easy to distinguish from planets because stars twinkle and planets don't. And you can learn the planets by learning just the sky and where to look. One of the tricks you can use with your sextant is to set it at 0 degrees, 0.0 minutes, aim it right at the star, get it in your telescope, and instead of moving the index arm to bring the body down to the horizon, you keep the index arm stable and you move the whole sextant to bring the star down to the horizon. That's one way to do it. Another thing you can do is some sextants have, instead of a telescope, just have a tube. Some people find it easier to use that because the telescope magnifies motion, and if it's kind of dark anyway and it's a low point of light, it can go zipping back and forth pretty fast through a narrow field of view, which is what you get with high magnification. But if you can see the star fine with your naked eye, then you just put the tube on the sextant and take the telescope out and look at the star through that tube, and again, you should be able to move the star, bring it right down to the horizon. It's a bit easier to do without that magnification if you can see it. Not everybody finds it as easy as that. The other thing you can do is use that device, that star finder, and based on the local hour angle of Aries, and you can find Aries, we were just looking at it a minute ago in the white pages, and you take the GHA of Aries, and then you subtract from it your longitude, and you get the LHA of Aries. And then you pick out the clear plastic disc that's our latitude. I think 35 is the closest. Plunk it over the white disc. The white disc is either north or south. We're in north, so plunk it over that. And then take the pointer and point it to the LHA of Aries. And every star that you can see will be shown. It will show you the altitude and the ZN. So let's say the star we had in mind had an altitude of 35 degrees and a ZN of 0.56. We set our sextant up for 35 degrees. We point it towards 0.56 degrees true, and there's a star there. Now the cool thing about the navigational stars, all of which are on this one white page for the date, is that none of them live right next door to any other stars. So they're far enough apart that if you set it for the right altitude, preset it, and aim your sextant in the direction when you see a star, that's likely to be the one that you're going for, okay? From that point, you work it out pretty much like with a star, pretty much like you would with the sun. So just like the sun has its GHA and its declination, stars work the same way too. There's just this wrinkle, and in order to keep this book this size, okay, and because stars don't move relative to each other very much at all, they're all related to this one arbitrary point in the sky called Aries. So for any day and hour, you can find the GHA of Aries, and that's in this leftmost column, okay? To that, when you go to the minutes and seconds, if you return to that, you'll see that Aries is that second column for the minutes and seconds. So you add for the minutes and seconds to Aries, and that gives you the complete GHA Aries for the day, hour, minute, and second. Okay, then it's just like the sun. You subtract your longitude, your assumed longitude from it. If the GHA of Aries is less than your assumed longitude, let's say it turns out to be, the GHA, I'm sorry, back up just a little bit. That's the GHA of Aries that you subtract your assumed longitude to find the LHA of Aries. What we're going to do now is find the GHA of a star. If you notice, if you look to the rightmost column, you notice all the stars in alphabetical order, and it gives you their SHA and their declination. So you start with the GHA of Aries, you add the minutes and seconds, and then you add the sidereal hour angle for the star, which is, you just pick whichever star it is. So on September 9th, 10th, or 11th, if we were to look for Betelgeuse, the SHA of Betelgeuse is 270 degrees, 52.5 minutes. Its declination is north, 7 degrees, 24.8 minutes. So we'd write those down. We take that 270 degrees, 52.5 minutes, and we add it to the GHA of Aries to find the GHA of Betelgeuse. Okay, that's what we subtract our assumed longitude from, okay? And so now we've got an LHA of Betelgeuse. And from that point on, well, it's pretty much the same in this book as it is with the sun. You go with the GHA of the LHA of Betelgeuse, and you use the declination that you just wrote down here, and you find an HC, and you find a D, and you find a ZN, okay? Now,
say that again?
Well, from what point?
This is the last sentence.
Okay, once you've written down the declination of Betelgeuse, and you have found the GHA of Aries, to which you have added the sidereal hour angle of Betelgeuse, you now have the GHA of Betelgeuse. You subtract your assumed longitude from that, and you have the local hour angle of Betelgeuse, at which point it's no different than the sun. So you go to the 249 tables, latitude 33, you go, is Betelgeuse in the same latitude as us, the same hemisphere? Is it contrary or opposite? And it's the same, I think, if I remember correctly. And not only that, and then you go into the range of declinations. Is it 0 to 14, or is it 15 to 29? You find which page you're on, then you drop down to the LHA, and you cross over to the declination, and it will give you an HC, a Z, and a D factor. And the D is for the leftover minutes of declination, because the column was whole numbers, but you got some leftover declination. It's really just like the sun, except with the sun, again, one more time, with the sun, you had a GHA of the sun, to which you added the minutes and seconds. You had a declination of the sun, and then a D factor to find its declination for the minutes. And then you subtracted your longitude for the GHA of the sun to get an LHA of the sun, and you use the declination for this table, and you cross-index your LHA with your declination. Same thing. Same thing for that star, and it's the same thing for the planet as it is for the sun. Okay? Question?
SHA is always added to the GHA of Aries?
Yes, it's always added. Now,
With a too high number, you just drop 360 off.
you can do that. Yeah, if the number's too high, just drop 360. Sometimes the number will be too low, it'll be too high, you'll drop 360, and now, oops, it's too low, it's less than your longitude, so keep the 360 there. So you can always, if it doesn't look right in that regard, just add 360 to it, it's going around and come back in the same place. Okay? So you can do the planets and the stars just like the sun, as each one an individual standalone site. And nothing stops you from getting up at twilight and shooting 3 stars and treating each one the same. Okay? And working this whole process through for each 3 stars as its own independent thing. So that would mean 3 assumed positions, 3 ZNs, you know, and so forth. There is a simpler way to do it, though, I think, and it's really handy, and that was why I passed out that sheet for volume 1. If you look at that sheet and you go to the page, which is the only page many of you have, which is latitude 33 north, what you'll see running down each side of the page is the LHA of Aries. And once again, that is the GHA of Aries, correct it for the day, hour, minute, and second, and then subtract your longitude from it to get an LHA of Aries, okay? Now, for a given LHA of Aries, on a given day, okay, what will happen is that you'll see for any one of these LHAs, look on the page in the column, and you'll see 6 stars. So let's say that it was 210 degrees. That was our LHA of Aries. We're latitude 33 degrees north. The stars for this LHA that they want you to look at or take seriously are Kochab, Vega, Rassilog, Antares, Spica, Regulus, and Dubhe. Okay. Some of those names are all caps. Those are the brighter of the 3. So if you just want to shoot bright stars, those are your guys. However, the others, the ones with little diamonds next to them, are 3 stars that their ZNs are roughly 120 degrees apart. So they make there's 3 angles in a wheel of stars, all equidistant. What does that mean? That means that the intercepts that you plot are going to cut each other at about 60 degrees to give you a good definitive position. So what makes this so easy? Well, first of all, to shoot stars at all, you've had to go through this process of predicting when twilight's going to be. So let's say that today twilight was going to be, I'm just pulling this out of a hat kind of, let's say it was going to be at 7:30, right, 1930. Okay, that's when civil twilight starts, when we worked it out. So let's give it a few minutes. Let's give it to, let's say 1734. And we're going to go to 1734, and let's say at that time, again, that we had an LHA of Aries of 210 degrees. Okay, and I haven't worked this out ahead of time, just sort of making this up. So with that, let's go to the first star, that's Kochab, and we'll see that Kochab is 48 degrees, 28 minutes, and it's got a ZN of 005. It's almost due north, right? So what we would do is we would say, okay, if it's at 7:30, I'm going to get Kochab right in my sights. I'm going to set my sextant for 48 degrees, 28 minutes, and I'm going to stare due north, and wow, there's a star. And as we work the star down to the horizon, we have somebody say, okay, I'm going to time you, and I'm going to say mark at exactly local mean time 7:34, or 1934. 30 seconds, 20 seconds, 10 seconds, mark, just like we do for a sunshot. And theoretically, you've got it down so that star's right on the horizon when they say mark, and then you say, okay, and you write down the HS at that time. And then you got 4 minutes between that time and the next one. Why 4 minutes? Well, I'll explain it to you. Antares is your next star. If we shot Kochab at 7:34, we're going to shoot Antares at exactly 7:38. Why exactly? Well, in 4 minutes, the Earth would have turned 1 degree, exactly. Our LHA would have gone up 1 degree, exactly. What does that mean? That means we can use the same assumed position, right? Because we're dealing with exactly the same numbers of LHA. The only difference is, instead of 210, when we get to Antares, we're going to drop down 1 LHA to 211. And Antares has an HC of 21 degrees, 1 minute. And it's got a ZN of 145 degrees, right? So roughly southeast. So what we do is we set our section up for 20 degrees, 32 minutes. We point to the southeast to about 144 true. There's Antares. And just about the time we get it lined up, we start working down the horizon. Then our trusty assistant is going, okay, you got 30 seconds, 20 seconds, 10 seconds, mark, and you write down Antares. Okay, now you got 4 more minutes to set up the next one, which is Regulus. And with that, you drop down 2 LHAs to 12 degrees. And same thing, Regulus is going to be 31 degrees, 50 minutes. The ZN is 253 or 260. Is it 260 or 263? We aim off in that direction. That's almost due west. And wow, there it is. And same thing, we bring the star down on the horizon right when we are at 7:42. The first one was 7:34, 7:38, 7:42, and we measure Regulus and we write that down. Okay. Now we could have done quite a bit of this ahead of time. We could have done this in the afternoon. We could have said, well, we're gonna be up and we're gonna shoot at exactly 7:34. And work out what the GHA of Aries is, what is the LHA of Aries, what assumed longitude, put that assumed longitude on the chart. We know we're going to shoot these three stars, so we take those 3 ZNs and we draw those lines ahead of time, right? Emanating from that single assumed position. They'll radiate out into 3 relatively equally spaced lines. Is there anything else we could do? Well, actually there is. Since it's a nice afternoon, we got plenty of time. If you recall from the Nautical Almanac, we've got to correct the HS for dip and main correction. We're going to subtract for dip, and then we're going to subtract from the main correction. Well, why don't we just find those now and add them to the HC? So that all we do then when we look at the sextant, we know right off the bat what the intercept is. It's the difference in minutes between what our sextant said and what that corrected HC said. Okay? Then all we got to do with that last star, or I guess it was Regulus, is get our dividers, set them up for each increment, and draw the perpendiculars to those 3 lines. And where they cross, where those lines cross, that's our 3-star fix. Literally within a minute of that 3rd star, you can have your fix on the chart if you want. That's why this is an easy way to do it. Does that all make sense? Okay. Now keep in mind it's going to be the same dip correction for each of the 3 stars because your height to lie is going to be the same. It's going to be 6 feet or whatever you're used to using. But the main correction does depend upon the altitude, right? So you need to bear that in mind, that each star is going to have a slightly different main correction. Then that's the number you'd add to the, you'd add that number along with the dip number to the HC you get from the volume 1. Okay? All right? All that makes sense? Okay. Very good. All righty. So we've talked about shooting a wheel of stars. We've talked about planets and how they're not much different. Okay, so the last thing we're going to talk about, and the squirreliest one, is the moon. Okay, so the moon, not only is it complicated because the Earth is circling the sun, and not only is the Earth rotating on its axis, but the moon is circling the Earth. And also, the moon is being pulled in odd ways by the gravity of the Earth and by the sun. So its behavior is erratic compared to almost everything else in the sky. The Royal Observatory went on the project of trying to determine longitude based upon time with the moon as a clock. It was tough because it kept speeding up and slowing down and doing this and doing that. So it was pretty hard to determine where the moon was going to be at any given time. It does operate with a regular cycle, but it's about 27 or 28 years, something like that. So it took an immense number of observations to be able to determine exactly where the sky was going to be, and therefore how far away from the specific stars was it going to be at any given time, to allow you to use the angle between the moon and a given star to be used effectively as a clock. Okay? We don't have quite the same problem as the Astronomer Royals did, but we do have a somewhat erratic body. But the good thing about the moon is, a lot of times you can see the moon at the same time you can see the sun, right, where they're both out. So if they're not like, if they're not opposite of each other, so that the intercept lines are not parallel or nearly so, if they're crossing each other at a decent angle, you can get an actual fix during daylight, which is about the only time you can really do that, an actual fix during daylight, either early in the morning or in the afternoon. So that it's handy for that purpose. It's also the case that the same periods of twilight that we're talking about for shooting stars and planets, there's no reason you couldn't shoot the moon also at the same time. Seldom do people do that because it's more complicated for the moon than it is for the planets, and it's certainly for the stars. But you can do it nonetheless, and it might be the case that you need to if maybe you can only see one star or one planet and the moon, and that's all you have. You just have two things up there, so you use what you have, and you go ahead and you shoot the moon. So there's that. So if we go back to the almanac and we look at September 11th, we see in the column for the day and the hour in the white pages, the moon column, okay? And just like the other things, we have a GHA, we have a V correction. It's not lurking at the bottom of the page now, it's right next to the GHA. We have a declination, and we've got the D, and it's not at the bottom of the page either, because the moon is too erratic to let a whole 3 days go by without, noting that change. And then we've got another thing called HP, which stands for horizontal parallax. So it sounds scary, but it's really not. It's just another factor in what we have to do to apply the correction. So we go for the day and the hour, and we do just what we did before with GHA and with declination. We write those down. We write down the V number for the day and the hour, and the D number, and then off to the side a little bit, we write down the HP, okay? Alrighty. So once we do that, then for the moon, we do what we always do. We go back to the minutes and seconds page to allow for the extra minutes and seconds and so forth. So let me dial that in right now. And if we go to say, 11 minutes, okay? As you'll see at 11 minutes, you'll see that, let's say if it was 11 minutes and 20 seconds, if you note, you'll see the moon at 11 minutes and 20 seconds was 2 degrees, 42.3 minutes. That's what you add to the GHA. Then you add the V correction to the GHA, and then you take the D correction and you also add that to the moon's declination. Now, again, you have to note whether the declination is going up or down. So if we look for September 11th, and we look at the moon, you'll see that the declination is south, so it's in the contrary hemisphere, and it appears to be going up this time of the year, okay? So it's that little d is positive. Okay, so we can find the GHA and the declination by taking the GHA, applying the minutes and seconds for the moon, then applying the V number. We find the declination for the day and the hour, just like we do with the sun, and we apply the D number, positive or negative, and we take note whether it's in the southern hemisphere or the northern hemisphere, because, it's not, we may not be doing this as often as the sun, so we may not be getting used to it. A question?
Yes, back in the increments of corrections.
Yes.
So there's some columns for sun, planets, and one for Aries and one for moon. And then there's 3 columns that all say B, or D.
Right.
Is that for this?
It's for any of those things. Those essentially what a V or a D is. It just tells you for each whole number increment what proportion of it's covering. So, the first little d, the little d that you're using here is the correction you apply to declination. In this case, whether it's the sun or the moon, that's what you do. The V correction is not applied to declination; it's applied to the GHA. Okay, so it's the same table we were using for the sun, and we are.
I think the question was. There's the planets, Aries, and the moon, and then there's 3 columns, but they apply to, the sun one is the first one,
No, that's not really it. If you notice, those three columns start with 0 in the upper left, and the numbers just keep getting bigger. You need 3 columns to get all the numbers in. At the biggest, it's like 18.0 at the lower right. So the 3 columns just allow you to go all the way between 0.0 and 18.0. So yeah, so it gives you the whole range that you need. That's its only purpose for dividing it up that way. Okay? Okay, so there you go. I actually think we're not going to work out one of these, because what I'd really just like you to do is just get used to the Nautical Almanac, and you're going to get one of those questions anyway. So what I'm going to do, are there any questions about the moon or about the planets?
Okay, on the very bottom here of the moon, okay, so we have the V's, and we have the D's,
yes,
and we figured out the same way if the declination's going down or up.
Right, right.
What's at the very, very bottom has like an SD 15, 50.
Right. That is semi-diameter, and that has to, and I haven't, thanks Alex, I haven't finished. I have one more thing to talk about the moon. I'm jumping ahead of myself. But you're not going to have to worry about that, actually, so don't worry about it. But you do have to worry about the last thing I'm going to tell you. That is, if you go to the very end of the Nautical Almanac, in the Roman numerals like 35, you will see altitude correction tables for the moon.
Like about what page is it?
It's Roman numeral 34 and 35. Okay, and all of the whole thing for this is simply, this is what you need to correct your HS into an HO. Okay, so you'll notice a couple things. One is that the upper column goes all the way across, the left page at 0 to 4 degrees, and then moves on to 30 to 34 degrees, jumps over to the next page at 35 to 39 degrees, and it goes over to the end of the page to 89 degrees, and then it follows. Well, actually, it doesn't, because it doesn't get higher than 89, does it? It can't do that. So, in any case, these are all altitudes of the moon. Notice, though, inserted in the middle here is a dip page. So the moon has its own dip correction, okay? Don't worry about it. It doesn't even show 6 feet, just use the same minus 2.4 if you're using 6 feet as you have been. So don't worry about that too much. But there's an explanation that says moon correction table. So what you do to correct your HS is you first correct it for dip, and then you've got apparent altitude. And there's a range of them. So let's say the apparent altitude of the moon happened to be, 30 degrees, 20 minutes, okay? So if you go across the table at the top of apparent altitude, you're in the range 30 to 34 degrees, okay? Drop down from 30 to 34, which is at the bottom. You'll see it goes 30, 31, 32, 33, 34, and in between, it gives you the corrections. So you're going to be correcting this. Oh, excuse me, wait a second. Wait. Yeah. So you're going to be correcting this in a column for the degrees, and then the minutes are over to the right. So let's say it was 34 degrees, 20 minutes, okay? You go to the 30 to 34 column, you drop down to 34, and then you drop down further to where it lines up with the 20 in the right margin, and the correction is 56.9 minutes. Okay? 56.9 minutes. Then you stay in the same column, and you have to determine, is it the lower limb or the upper limb of the moon? Now, with the sun, if you usually can see the bottom, you can see the top. But because the moon, you only see part of it at a time sometimes. Sometimes you can't see the entire top of it or the entire bottom of it. So what you need to do is you then decide whether you shot the bottom or the top, and then you drop down in the same column to the closest number to the HP. Remember the HP number we wrote down from the white pages? Okay, and that gives you your correction depending on if it was upper or lower. All these corrections are added to the altitude, okay? So they're all positive. However, if you shot the upper limb, you have to subtract 30 minutes. Okay? If you shot the lower limb, you're cool. But if it's the upper limb, you have to subtract 30 minutes. So you take the apparent altitude, and then you correct it for the dip, and then you do the upper page for the correction, the upper part of the column, and then you drop down depending on upper or lower limb, and you use the HP. It's the explanation they give you in the almanac is really pretty clear. All this is, it's a way of doing the basic information, just like we did with the sextant, taking an HS, applying the dip correction, applying the main correction, you got an HO. It's just that the main correction is a little bit more complicated, that's all. Otherwise, it's the same as the sun, really. Okay? That makes sense? Yeah, I know it's sort of, but it's again, what I would do in actual practice is I would do everything else a few times before you did the moon, and then it'll come as second nature, really. But they do give a good explanation for the main correction for the moon. And you won't see, if you look on this first page in the almanac, you've got the sun, you've got stars and planets. They don't tell you the moon, right, for the main correction because it's contained in that other section at the back of the almanac. All right? So if you were to do this in practice, you go, okay, wait a minute, I can't find the moon here. Oh yeah, I got to go back to this Roman numeral page. You do that, you look it up, and it's kind of, it explains it pretty well. That it's all only about the main correction. Okay? Like you did to begin with. The mid-latitude is 33 degrees north, and the easternmost longitude is 117. Okay?
Easternmost?
Yeah, the easternmost is 117 degrees west. Okay, the first thing you're going to do is you're going to predict the time you're going to be taking the noon sight. So you're going to predict the time of local meridian passage for September the 14th. And you're going to assume for that, at the time you pick, it's going to be longitude 117 degrees, 30 minutes west. Okay, is the time you're predicting about noon will occur. Right, that's number 2. 3, you make a series of observations of the sun beginning several minutes before the time of noon is predicted, in the question you just answered, and the sun's measured altitude of the lower limb remained the same for 2 minutes before and after the predicted time of noon. You had an HS of 59 degrees, 51.0 minutes. The height of eye is 6 feet, and there's no index correction for the sextant you're using. Those two things, the height of eye and no index error, will remain consistent with all of these questions. The question is, what is your latitude? Okay? All right, you draw your latitude line, and you mark that at whatever time it was you predicted this would be, and then you proceed on a course of 315 magnetic. Note that's magnetic, so you're going to have to make the conversion.
315?
315. We're assuming there's no deviation. So 315 magnetic, you're going to have to convert that to true. You're going to go on that course, so you actually need to know what the variation is in our part of the world, but I'll give you a hint here, it's 11 degrees east, okay? So you proceed on a course of 315 magnetic from the time of the noon sight at a speed of 6 knots. At 1514 local mean time, you make an observation of the sun. The HS is 43 degrees, 39.4 minutes. What is your position by running fixed? So you're going to have to advance that line of latitude along that course and that calculated distance to get the fix where those two lines cross.
And we're making all these on the
Plotting sheet.
plotting sheet.
Yeah.
The HS was
What's that?
what did you say the HS was?
The well, it's on the page.
Oh,
here.
I see. Oh.
Yeah, everything's here. I'm just reading it from the page that you have. Okay, then what you need to do is you need to predict local mean times for the evening twilight at the above position. And since this comes in 5 degree, in the almanac, every 5 degrees, just use 35 degrees north for your prediction. Okay, at 19 hours 30 minutes local mean time, you make an observation of Polaris. The HS is 33 degrees, 00.8 minutes. What is your latitude? Okay, then 4 minutes later, at 19 hours 34 minutes local mean time, you make an observation of the star Arcturus. You have an HS of 34 degrees, 06.8 minutes. What is your position at 1934 minutes local mean time? Okay. Number 8, alternatively, you decide, using volume 1, you're going to predict the optimum selection of stars to use for a 3-star fix during that same evening twilight, with 4 minutes elapsing between the first star shot at 1930 LMT, with a second at 1934, and a third at 1938. Plot the 3 azimuths from a common assumed position and pre-correct the 3 respective HC values for the dip and the main correction, so that you can obtain the intercepts almost immediately after making the observations to plot the fix. Now, I'm not giving you HOSs here or anything, so we're not actually plotting the fix. You're going ahead and you're pre-correcting the HCs though, okay? So, so that when you do take the observations in this hypothetical example, you'll be able to plot it pretty quickly. Okay, it's still September 14th, 2024, local mean time. What is the HC and the ZN of Saturn at 19 hours, 36 minutes local mean time? Okay, so now we're going to skip ahead to September 16th, but we're still at or near your position on the evening fix of the 14th. What is the HC and the ZN of the moon shooting the lower limb at 19 hours, 40 minutes local mean time, using those moon pages that we just talked about? And actually, you don't really need to, you really don't need to do that main correction, do you? Because I'm not giving you, oh yeah, actually you do. That's the next question. If the HS of the moon, lower limb, taken at 19 hours, 40 minutes, is 14 degrees, 26.7 minutes, what is the HO? Okay. All right. Okay, that all seems straightforward? All right, so much for the navigation part. Now we get to the easy part. 3rd century Greek mathematician and astronomer who with one observation both measured the size of the Earth and invented the noon sight for latitude. I'd like to see a diagram of how he did that. Who was he? How did he do it? What was the name of the Spanish institution that attempted to professionalize the practice of navigation and also keep geographic information a classified state secret? And if you want to pretend this is Jeopardy, you can say what is, you know, at the front of it. What 2 navigational instruments of the early modern era use gravity instead of the horizon as an index from which to measure the altitude of celestial bodies? 15, what institution functioned as the greatest military industrial complex of the medieval Mediterranean world and also as the working example for the origin of engineering science? Who translated its practices into the founding document of engineering? 16, what English admiral wrecked almost his entire fleet at the entrance of the English Channel in 1707 due to navigational error? Number 17, the cross-staff measured the altitude of celestial bodies above the horizon, but proved dangerous to eyesight when used for the sun. What instrument supplanted it? Number 18, what English institution emerges as the first example of state-sponsored big science with a dedicated research program intended to solve a technical problem? 19, what English admiral captured the richest single prize in history, but lost 90% of his men and almost his entire fleet just getting to and from the scene of the action? 20, who was the famous horologist who not only invented the first truly practical time-keeping device sufficiently accurate to determine longitude at sea, but also established the basis of modern for-profit scientific technological research? 21, what famous English astronomer was also a Royal Navy captain who rode the Atlantic in an effort to use magnetic variation to determine longitude? 22, the quadrant, later called the octant, was the primary optical navigational instrument from the late 18th century to the late 19th century. But today, only the sextant is in manufacture or widespread use. Why is that? Who was a high navigator priest of Raiatea who sailed with Captain James Cook in HMS Endeavour as his translator and navigational advisor? Well, that's going to be in tonight's talk. So, and then finally, what early modern instrument combined with a tabular rule for the North Star could determine both time and latitude? Okay. And interestingly, Cook, he is widely regarded as the greatest Western navigator who ever lived, even though every single thing he was assigned to do, he really never did. So he never actually observed the transit of Venus because the atmospheric conditions weren't really good for it. The sun isn't a precise disk anyway, so that whole idea was a nice idea, but it really wasn't very practical. Second, he never found Terra Australis Incognita, for the good reason that it isn't there. Oh yeah, but he that's right. He wasn't the first person to find Australia, but he did bump into Australia pretty hard at one point. But that wasn't. But it wasn't what they thought Terra Australis Incognita was. And then of course he never found the Northwest Passage either. And even though he was really good at navigating and he was the cutting edge for things like tables for lunar distance and longitude, Cook was awarded the greatest scientific award of its day, the Copley Medal, by the Royal Society, but it was because of his work in scurvy. Even though Cook himself never knew what caused scurvy or what would cure it, only that you eat as much fresh food as you possibly can and you can stave it off. And ultimately, as I said last time, that may be one of the things that led to him getting killed, because they were just eating the Hawaiians out of house and home until they finally got tired of the visitors, and Cook bore the brunt of that, along with a few of his men that got caught when he did. But there was this point where the Endeavour was the furthest reach of Western technology and the furthest reach of the Enlightenment. And as when Cook went to Tahiti to observe the transit of Venus, that required a working relationship with the Tahitians. He was really good at establishing that. And then after their efforts to observe make the astronomical observation, the Endeavour continued to roam through the South Pacific. And he took with him, this is your test question, he took with him a guy who was the high navigator priest from the island of Raiatea, the most sacred island in all of Polynesia. Its old name was Hawaiki, and the oldest marae or temple in all of Polynesia is the temple of Tapu Tapu Atea, on the island of Raiatea, from which all Polynesians believed all of them descended. Even though that probably isn't true, spiritually, that's kind of the center of their universe. Well, Tupaia was a priest of that marae and was also a high navigator priest. And he went with Cook along with another Tahitian, and he began to translate for Cook, who's there also as a translator for Cook, should they run into people that spoke the same language, and also because Tupaia had intimate knowledge of all these islands in the South Pacific where the Endeavour was headed that neither Cook nor any other European had really seen or understood. It turns out he had a fantastically detailed knowledge of them. Anyway, so you have this interesting moment in time where the greatest Western navigator who ever lived, so many of us believe, happened to be sailing on the same ship with a great navigator from an ancient tradition of navigation that may be the most sophisticated system of wayfinding human beings have ever implemented. So it would be amazing to be participating in that. What they found was, as Endeavour sailed through the Pacific, was something on the order of a great mystery. All of these islands they went to were inhabited by people who spoke the same language. They all seemed to come from the same ethnic stock. They had the same belief systems. They had the same social structure, the same technology, and they were strewn over thousands of miles of open ocean. Well, how did they get there? Well, when Cook asked that question, I said, well, we came from a distant land far in the east, but otherwise we sailed there. Well, Cook believed that, and he had Tupaia as an example because Tupaia knew the names of all these islands that they were finding, and he knew how to find them what direction to sail. Interestingly enough, Tupaia had a hard time digesting or internalizing the system of navigation that we've been learning that Cook used. And when Cook and Joseph Banks asked him to produce a chart that had all these islands on it, he produced this map, since called Tupaia's map, which is one of the most strangest documents in the history of navigation because there's about 80 islands on it, and they're all there, but the relationship to each other is completely jumbled. And so that was thought by many people as evidence that they actually didn't know where the hell they were going. They just found their way, they just populated all these islands by accidental drift voyaging or something like that. As it turns out, Tupaia's map, it was impossible to reconcile his understanding of space, geographic space, into a Western understanding of space, or a relative reference system of navigation into the absolute reference system that he was being asked to produce, but which that society had absolutely no, it wasn't part of their culture. It wasn't part of their way of understanding the space they moved through, or even depicting reality as they saw it. So this great mystery ensued. Where do these people come from? It might have been established easily had they found voyaging canoes in Tahiti and other places, but all voyaging to distant islands had stopped about 700 or 800 years before Cook got to Tahiti. So he never laid eyes on an oceanic voyaging canoe, and almost no Westerners ever did. That, again, leading to the further mystery of where do these people come from.
You said 800 years?
700 to 800 years, yeah. There was this rush of voyaging between about 1000 BC and about 1200 AD. So let's say 500 years or so before Cook.
Dr. Ash?
Yes.
Has there been anything done to try to establish why did they stop voyaging?
That's a good question, and there's not really a good explanation for it. I suppose they found everything, and nothing more to find. I don't really know the answer to that question. So, in any case, in the efforts to do so, looking at how we trace this, there is in looking at the geography of the Pacific, there is this line that goes down the Pacific called the, I'm going to read this correctly, the Andesite line, and everything on the line or to the east of it, there's a different, the islands tend to be high islands, mountainous, rugged, fairly new geologically, they're volcanic, they're rising up from the ocean. It has to do with the tectonic plates. Everything to the west of that line, the islands are much older and they're actually sinking. So that tends to be forming reefs and lagoons. So as far as an ecology or an environmental sort of system, these two different kinds of island types provide entirely different sorts of environments for people to live in and try to survive in. So you can see what happens with a high island when it starts to sink, as we see here in this example. As it starts to sink and go down, these islands all have fringing reefs around them, or at least the ones in the tropics do. And as the island begins to sink into the bottom of the ocean, those reefs, which are composed of living things and corals, continue to grow to touch the surface. Ultimately, there's very little of an island left, as you see in the middle island there, Bora Bora. And then finally what you're left with is the island has disappeared entirely, and you have the ring of coral around it, which forms an atoll. So a patch of emptiness in the middle, this wall of coral grows up straight up out of the ocean, and there's nothing in the middle. So each of these are dramatically different kinds of environments, and it produced kind of different cultural responses. The other environmental factors having influence over how these people were distributed have to do, of course, with the winds. And this is the pattern of trade winds that prevails most of the time due to the Earth's rotation and Coriolis force. The Pacific High generates a clockwise circulation of air, of wind, that brings the wind from the northeast in the North Pacific around and finally around to the west above the Pacific High. So we're kind of there in that western portion, which is why our winds typically come from the west or the northwest. The mirror image of that exists in the South Pacific, where there's a South Pacific High, and it generates a counterclockwise direction, and the wind, the prevailing trade winds there come from the southeast. In the middle, where these two join, is another area of high pressure, and where the air is going up, and that's an area of alternating with calm winds much of the time, with squalls and variables and things of that nature. It makes it very difficult to sail in or move from one to the other. On the other hand, during some years, particularly El Nino years, that trade wind pattern can shift entirely, and the wind can blow to the west, including during summer, which means it sets up the possibility of navigating by running downwind from east to west and then returning. There's not a lot of evidence that was done much in long-range navigation, but at least it set up the possibility the wind isn't always blowing from the same direction all the time. Augmenting the flow of the winds are the currents that dominate the Pacific, and as you can see, they're pretty similar to the winds. But the winds are the dominating factor. The currents, even the ones that are fairly strong, are moving at maybe a knot and a half, 2 knots, or to say 2 knots at the most. That would be going really strong. But mostly it's the wind that we're talking about here, and the ships were, any vessel that was going to cope with the distances crossing the Pacific would have to use the wind to do that. People did it, paddle boats across the whole Pacific. So we believe that the pattern of migration from humanity roughly followed this pattern here, and this is a bit out of date. Jim Cassidy, one of our docents and one of our crew members, has a much more up-to-date version of this. But essentially we have humanity coming out of Africa about 250,000 years ago, up into Europe about 40,000 years ago, crossing over into Asia, Asia Minor 100,000 years ago, and then continuing on down to Australia, where they would have had to have some kind of oceanic technology to get to Australia, the 50,000 years ago when they did that, and then across Asia, 40,000, and into the Americas about 12,000 years ago. Now, 12,000 years ago is a date for Folsom and Clovis culture. We now believe that there have been people in the Americas for longer than that, as long as perhaps 20 or 30,000 years. And not only that, a strong possibility that they didn't cross the land bridge from Asia to the Americas when during a glacial period, so much of the water was locked up in the glaciers, and you had an all-land route to get across from Asia. The consensus now seems to be that it was a maritime route, and that all the indigenous, or most of the indigenous peoples in the Americas, came across in these epic voyages from Asia, following what's now called the Kelp Highway down the west coast into the Americas and on to, to populate the rest of the North and South American continents. Interestingly enough, there are 6 language groups found among the indigenous peoples of the Americas. California is the only place where all 6 are found. So everybody, one point or another, goes through California. So there you go. So
Still true.
what's that?
Still true.
Still true, yes. Yeah, it's just, they're all going to Disneyland. So Europeans right off the bat began to concoct ideas about where these people came from. You know, the Polynesian peoples encountered by Europeans seemed to them extremely admirable people. They represented to them some of the best of like ancient Greek or Roman culture. They lived in a paradise situation. They were physically attractive. They were big and powerful people. They had this sort of idealized feudal society. Didn't seem to be quite so uptight sexually as Europeans did, and they didn't seem to have the excesses of wealth and poverty that characterized Europe. So the Europeans thought, well, maybe they're the descendants of ancient Greeks and Romans, and that indeed was the popular way that that Europeans envisioned them, and sometimes they gave them names from classic literature. And when they took, when they had travelers with them from Polynesia and they took them back to Europe, they liked to dress them up in these sort of romantic ancient costumes, or what they thought they were. This particular guy was Omai, who was taken, who was a Tahitian who Cook brought back to Europe on the 2nd voyage and then deposited back in Tahiti on his 3rd voyage. After a while, though, that occurred to them that, these people, they don't have columns or buildings that look like Parthenons and pyramids and things like that, and they don't actually have a language that bears even the slightest resemblance to Greek or Roman. So they gave up that idea, and then it became popular in the early 1800s to think that these people were just one of the lost tribes of Israel that had just wandered across Asia and then out into the Pacific somehow. And then there began to be a popular notion that these were Proto-Sanskrit speaking Indians, Aryans, and that was a popular idea that they came from India or East India, and that was popularized by an anthropologist named Edward Trigger in Aryan Maori, in a speculative treatise he wrote in 1885. But they still didn't really have any good idea of where these folks came from. It turns out that the cultural area that we're talking about is the largest area on the surface of the earth inhabited by people speaking a similar language or from a similar language group, and having the same technology. So if we look at the span of the Austronesian language family, that includes Polynesia, but it also includes Micronesia as well. It goes from all the way from Madagascar all the way to Easter Island. It's a vast area, entirely oceanic in nature. And interestingly enough, it's the same place. You see the same kinds of voyaging canoes, the same kind of watercraft that prevail over the same area. So those particular watercraft were obviously the enabling technology that allowed these people to go over these vast distances. Well, they're not just vast distances. Many of these places who are inhabited are tiny specks within a vast distance, within a vast area that's otherwise totally empty. And if you don't know how to get from one place to another very well or have a sophisticated system for doing it, it's a pretty risky endeavor, because if you miss that little island, you know, you're going to die of starvation or lack of water or so forth. But nonetheless, it was an amazing achievement that they were able to do this. Now, one of the ways that the pattern and the sequence of colonization of these islands was traced was through archaeology, and finding this sort of signifying or indicating type of pottery from a place on the northwest coast of New Guinea called Lapita. It's a particularly distinctive kind of pottery with a distinctive design and fired in a particular way, and it's called Lapita-ware. And as the early Polynesians came down the Asian archipelago and into New Guinea, they stayed for quite some time, even though there's a very little Polynesian trace now in New Guinea. They stayed long enough to develop this kind of pottery that they took with them on these canoes throughout the Pacific. Well, pottery is kind of fragile, it doesn't last long, so you don't find these things throughout Polynesia, but its presence in different places going from east to west, or excuse me, from west to east, the stratigraphy of that, showing the periods of time over which the sherds of pottery were distributed, suggested the sequence from west to east. So what's interesting about that is that that's contrary to the trade winds, isn't it? Contrary to the currents. So if they were moving by these oceanic vessels, they were doing so against the prevailing winds and the currents mostly. Manish, did you have a question? Oh, okay. So this is an example of Lapita-ware from the Peabody Essex Museum. And this is the kind of thing that they would find in middens and things of that nature. Yes. Okay. You're a big fan of the Port of San Diego.
Yeah, we love them, but...
Well, I figured we had the 2 cones there and it was ours, so... Yeah.
Okay.
Should we give him a minute to...
Yeah, well, I'm just gonna, I'll keep going, but we'll continue on. So in any case, so generally speaking, the progress of Polynesians pretty much this had been established by the 1960s or 70s. But basically, you could at least trace the pathway from New Guinea through the eastern Polynesian islands to Santa Cruz Islands, Vanikoro, Fiji. So the Polynesians were in Fiji for a while. They moved from Fiji to Samoa and Tonga, and there you see the first really truly Polynesian cultural establishment. From Fiji and Tonga, east to the Society Islands, and then from the Society Islands, you had voyaging that went down to New Zealand, about the year 1000 AD, across the Pacific to Easter Island, and the islands in between, Mangareva, and the Cook Islands to the south of the Society Islands, up to the Marquesas, and then the Hawaiian Islands were colonized from two different voyaging periods, from the Marquesas up to Hawaii, and then somewhat later from Tahiti to Hawaii. And for a while, apparently, there was regular voyaging taking place between Hawaii and Tahiti. So,
Dr. Ashton,
yeah.
It seems really interesting that they seem to have avoided Australia.
Yeah,
They're
yeah.
giant landmass.
Yeah. No idea why. But there were people living in Australia, had been living there for 50,000 years.
Yeah.
So it may have been just that they were interested in going to places there wasn't anybody living already. Could be. That's a good question, and I can't say as I have the answer to that. So in addition, though, to that triangle, that Polynesian triangle, there are outliers. So for instance, over in the Melanesian area, you have Anuta, Tukopia, Ontong Java, Reno Island, Bellona Island, and Ontong Java up in the Solomons. Those are islands well in the middle of Melanesia. They probably were colonized very early, and they remained Polynesian ever since, for thousands of years possibly. David?
These folks are making extremely long sea voyages in voyaging canoes that are not terribly fast, and they're going upwind. And these people are presumably as susceptible to scurvy as Europeans. Do we know anything about the effect of scurvy on these folks?
Well, they would be just as susceptible, but they apparently, there's certain, and we'll get a little bit into that, there's certain foods that last a long time and can be kept fresh a long time that will stave off some of the elements of them. It's not, I'm not sure it's true that these aren't fast vessels. Some of them can sail pretty quickly, or we're known for being able to do that.
You mentioned going upwind.
Going upwind, yeah. Well, they can make way to weather, or they could, evidently. And as it turns out, it's actually much safer to be voyaging to weather than it is to be going downwind, because let's say it takes you 4 times longer to go back up to windward as you would to downwind. Well, if you were going downwind, you couldn't, and you would only be able to go about 20% of the way through your food supply, and then you'd have to turn around. But if you were tacking into the wind, it's always an easier run to come back home. So it's a little bit less risky to do that. And if you're tacking, you're covering a wider swath of the ocean. So if you're doing exploration or surveying or trying to find an island, you're covering more ground naturally that way as well as sailing a straight course. Now, when we talk about outliers, there have been some recent DNA studies in the Pacific Northwest that suggest there are certain Pacific Northwest tribes, the Haida notably among them, that have a lot of Polynesian DNA. So it's pretty clear that they actually made it to Polynesia. Thor Heyerdahl had the idea that because you could only go downwind, all the Polynesians had to come from South America. And so he built this raft, the Kotiki, to sort of drift downwind to the Tuamotus. And he did this because there were common plants, like the sweet potato, that are found in Polynesia, and not further to the west, and also found in South America. And there were also cognates in South American languages that you could find in Polynesian. However, so it's clear that there was contact between Polynesia and Chile, but it probably was not South Americans sailing to these islands. It was probably islanders sailing to South America. Okay, so almost certainly that triangle was a lot larger than we think. At this point, I'm not sure if I say this in a further slide, but at this point, the consensus is that the very first Polynesians probably originated in Taiwan. Okay, that's the birthplace of Polynesia, and probably the place that their legends and ancient tales refer to as Hawaii, someplace far to the east. Okay, but that would have been thousands of years before these major voyages in the Central Pacific. So there are plants from Southeast Asia, such as taro, breadfruit, the paper mulberry that's used for making fabric. There are also commonalities all throughout this area of religion. The Polynesians universally believed in this spiritual power called mana. It's kind of like the Force in Star Wars, right? It's this belief that that there's a spiritual power that inhabits everyone and everything, and that your status in society is a factor of how much of it you have. It's a little bit like electricity. It can flow from someone with a lot of it to not much. So the higher you were in social standing, the more isolated you were from everyone else, because if a commoner touched an elite or a high up person, the mana would flow there. They were also very keen on preserving the body parts of deceased people, because you would, particularly skulls, because you would preserve the mana there also. And most Polynesian societies practiced cannibalism, okay, because it was a belief that if you ate the deceased person, that is how you retained the mana that person had. They believed that there were spiritual places that were particularly resonant with spiritual power, and these were the sites of their maraes or their temples, which really were platforms made out of volcanic rock. And they also believed that there were just things that you didn't do, that you couldn't do without violating the preferences of the gods or the order of nature. It was taboo, or taboo is the word. And so there's sets of rules that govern people. They were governed by their social structure, and they were governed by their sets of religious beliefs. So it wasn't quite as free and easy a society as it seemed to the first Europeans that encountered it. They did practice human sacrifice as well as cannibalism. And most of these islands, when they were first occupied by voyagers, the populations grew dramatically and pretty quickly grew to a size that that island couldn't support anymore. And so that was one reason for voyaging, always trying to go to some new place to colonize, because the resources in their present place were tapped out with the number of people that were living there. Also, most Polynesian religions practice female infanticide as a way of controlling population. So they killed baby girls as a rule. So always were fewer women than men. The social organization was feudal. European societies are typically patrilineal in both inheritance and in identity. So identity and possession usually flows from the oldest male in a family to his son. All right, and then sons number 2 and 3, well, they're kind of left out of the whole thing. Everything goes to the oldest son. And number 2 goes in the military. Number 3 becomes a priest or something like that. But in any case, in Polynesian societies, they were bilateral. So status, relationship, wealth, and connections went both through the patrilineal line and the matrilineal line. It was one of those rare instances. There are a few societies that are matrilineal in both of these things, where women have the status and it's their family name that persists, and it's their family lineage through which property goes through. Now, in many of those, it doesn't necessarily go from a woman to her daughter. It might typically go from a woman to her brother's son. It's matrilineal, but the guys are still kind of controlling things in many of them. But in Polynesian society, it was a lot more egalitarian or gender equal, and women could be just as high status as men. Women were navigators. They were priests also, and they were royalty. The 3 layers of society. The Tahitian words were ari'i, the Hawaiian version of that is ali'i, and they were the royalty. And then there were the nobility, the ra'atira, and the ra'atira were landowners, so they were like feudal lords and so forth. And then finally, the tatiru or titi were commoners. So not slaves so much, but they were really the possession of the land. And so whoever ruled over that land actually had control over those people that were living on it. There weren't too many cases where a king or overruler would rule an entire island. Instead, because these islands typically, being volcanic, you would have all of these different environmental gradients between the edge of the ocean and the top of the mountain. Different plants that would grow up high. Down low, you could catch fish in the lagoon. You go outside the pass of the lagoon, you could catch different fish. You grew taro on these flat areas that could be easily irrigated from the rivers that came down through the valleys, and you could grow other things higher up. And so there was all this range, and so it was typically the case that these clans ruled over by royalty or nobility would occupy an entire valley from the water's edge up to the height of the mountain. And because these valleys often were quite the mountain ranges separating them were quite sharp and rigid, that made them also fairly defensible as well. You see this particularly in places like the Marquesas. So Tu was a famous king of Tahiti Nui upon Cook's arrival, Tahiti Nui being the larger of this kind of $2 island sort of thing. And then finally, the other thing that governed their behavior, one of the things that governed their behavior was just war. Polynesians were constantly at war. They were always fighting over resources, which were always scarce. They were fighting for control of land, control of the water, all of the various forces that were arrayed with one another was such that it was almost never the case that one particular clan got control of an entire island. It really wasn't until the advent of the Europeans when suddenly these warlike hierarchical feudal societies got their hands on European weapons and European expertise when they began to actually behave like imperialists. So that King Kamehameha, for instance, unified all the Hawaiian islands except for Kauai by the use of European mercenaries and weaponry and even European ships and so forth. So it took an existing paradigm for war and it amplified it significantly. War had its ritual purposes. It was often very symbolic, and seldom did societies fight to the death. Often war was conducted with ambushes or ritual displays. And so the famous haka of New Zealand was an attempt by one group of Maoris to intimidate another group of Maoris, and showing how fierce they were. There were ample opportunities for trade because these islands do produce different kinds of things. There are different kinds of animals, birds, flora, and fauna. So for instance, the birds that generate this red kind of feather were extraordinarily valuable, and the feathers themselves traded throughout Polynesia, and that color red was a symbol of royalty and of mana. There was a common set of aesthetics that governed them. They had a similar sense of artistic value. They had similar designs for all their tapa cloth. Their canoes had similar designs. Their tattoos and things of that nature were common throughout all of Polynesia. And they also dance and song and performances, particularly in Tahiti. There was this highly sophisticated performance society called the Ariori Society, which is, I guess, rock stars, I suppose I would say it was similar to. But they would go around and do these performances to all of on all different islands and in different valleys. The one weirdest outlier of Polynesia was Easter Island because it was so isolated. Easter Island was the only island that had these sort of monolithic statues called moais. And Easter Island was the only island we know of that had a written language. There were no other Polynesian islands that had written languages. Question, John?
I know they were doing trade, but did they have any type of monetary system? Shells?
I think it was mostly bartering, and I think there were, my guess is that there were kinds of shells and things like that were part of the barter system, but I'm not sure if it had the same function in the same way as we use currency for. But I think it was mostly barter. So anyway, Easter Island, very odd, strange place compared to other places in Polynesia. And it's interesting in other ways as well. Polynesia, where the Dutch explorers Schutten and Lemaire in the early part of the 17th century. And from this episode, I guess the first encounter wasn't a particularly happy one because they're shooting at them. I guess they're trying to get their quick canoe to stop. Well, this canoe that you see here, of course, they could outpace any European watercraft of the day. They were relatively fast, and they astounded Europeans in their ability to cover distances pretty quickly. There were a lot of similarities for the canoes. The islands groups each had certain distinctive kinds of canoes. What was interesting, and particularly the ones that were double-hulled, that were the voyaging canoes, is that the hulls were asymmetrical. They were, I want to make sure I get this right. They were convex on the outside of the hulls and concave and flat on the inside, so that whatever hull was to leeward would develop lift and help the vessel get to windward. Some canoes in Polynesia were single-ended, like our boats are, which is to say they were steered from the stern and they tacked to windward. Others were double-ended, and they had to shift the rig and the rudder from one end of the ship to the other as they kind of shuttled back and forth and working their way to windward. Some of the most valuable things that were traded were things like volcanic rock like obsidian, or the very, very hard volcanic rock that is capable of being used for making adzes, projectile points, and so forth. Because with this kind of material, you can then make canoes. Interesting, here's a picture of a Polynesian adze that's about 1,000 years old up in the space shuttle. So they get around everywhere. In any case, the way you make a canoe is you pick a tree. All the trees have names, And every tree in one of those islands has a name and is owned by someone. They decide to fell it, and then they carve it out. So the canoes were mostly dugouts, although their sides were often built up with planks, and they were very finely shaped, using a whole toolkit of drills, adzes, axes, and things of that nature. So it was probably the most complex and sophisticated technological construction that was taking place. There was the creation of all of these canoes. And building them was the province of a particular order of builders, a semi-religious order, and they had to be apprenticed into the order and spend years learning the trade, just like navigators did over a course of many years. And of course, it took a lot of work. What all of these canoes represented a significant investment in time and resources that could be spent otherwise used gathering food and other things. So these things were really, really important testimonies to the culture, and they were extraordinarily proud of them. And they remain so. So, of course, what happened is that all of these islands had Europeans encounter them, and there was quite a shock to the system. In some cases, Polynesians were able to incorporate European weaponry and military styles to build empires or capture entire islands. But the overwhelming issue really was disease, because these people had no natural immunity to European diseases. So it's typically the case that within a generation, or at most two, after contact with Europeans, up to 90% of an indigenous island population will be wiped out to disease. Things like measles, smallpox, typhus, syphilis, things of that nature. These people lived in isolated islands for eons and just had no resistance whatsoever or immunity to the whole bevy of Europeans, disease that Europeans had from intermingling between Asia and Africa and Europe.
Were there any instances of just the opposite, of Europeans getting diseases?
Generally speaking, so that's a really good question. So Europe and Asia and Africa, people have been in contact for thousands of years. And so there were no natural disease gradients between them. And so whatever was there was, and it covered vast distances of longitude. The oceans themselves provided significant disease gradients, so that there were indigenous diseases in the Americas, for instance. Syphilis was one of those, but not too many. And also the Americas is a north-south orientation. So, and there wasn't quite the same contact even in the Americas, so that the Incas didn't even know about the Aztecs, so much less about Europeans and so forth. So when Europeans got to the Americas, by 1610 or so, about 90% of the indigenous peoples in the Americas were wiped out. There were diseases, though, from the Americas, so syphilis made it to Europe pretty quickly within a generation. And syphilis, in its first iteration when it hit Europe, was, it didn't take a long time for the symptoms to manifest. It happened really fast, and it was really devastating. So it was a really, really much more virulent, dangerous, and communicable disease in the early modern era than it has since become over time. But mostly it was Europeans and their diseases, encountering the indigenous peoples in these places that basically Europeans had a lot of natural resistance to almost everything, as did Africans, as did Asians. Not so much islanders or Americans. So it was a catastrophic thing, and culturally extraordinarily traumatic. So in many respects, these people kind of lost their culture. They lost, not only had the tradition of voyaging been lost, but following shortly upon the discovery of these islands, Europeans found all kinds of uses for them. They made great whaling stations, and they were deemed really good places to proselytize and send your religion to. And so the London Missionary Society and other missionary groups from America and England would go to all these islands and Christianize them, and basically work hard to convince the Polynesians that everything about their culture was wrong. They should stop speaking their language. They should be wearing wool clothes. They should live like Europeans, which killed more of them probably when you get down to it. So in any case, this is just an example of different canoe styles and different methods. These are tacking canoes, where in a single outrigger, the outrigger is sometimes always kept to windward, and in a shuttling canoe like this, where the outrigger is always to windward. So and this is a case where it shifts. So we began the sort of trying to figure out where all these people came from and how these complex, sophisticated sites developed with this document here, and that is Tupai'a's map. And so it was a very mysterious document for a long time. It was deemed evidence that Polynesians might have known names of islands, but didn't know where they were. And so, and this prevailed all the way through the 1950s and 60s. Now in the 1930s, there was a anthropologist, a New Zealand anthropologist named Peter Buck. His Maori name was Tarangi Hiroa, and he wrote a book called The Vikings and the Sunrise. And he had translated a lot of the ancient chanties and poems and stories of Polynesians of all over Polynesia, and understood that these stories actually contained sailing directions, that these actually were the record of long-distance voyaging, and wrote them up in this book called Vikings and the Sunrise. Well, that book was ridiculed by archaeologists, or anthropologists, and mathematicians. One particular astronomer named Andrew Sharp just totally ridiculed it and said there's no way that these people could have possibly known where they were going. It was either guys that went fishing and didn't make it back home, or people drifting from one island to the other, or accidental voyaging. Cook himself thought that these people actually were navigators, or had been navigators, and knew what they were doing. He didn't know what to make of Tupai'a's chart, as no one did, but then in the early 1970s, anthropologists began to start doing field work on islands that had not been contacted, or not been heavily influenced by European contact, in places like Tikopia or Satawal or Pulawat, and began to document these guys navigating hundreds of miles without any sort of instruments or mathematics or charts or metallurgy. A book called by David Gladwin called East is a Big Bird was probably the first one to bring people's attention to it. In 1970, an anthropologist, his name will come to me. In any case, this guy got a hold of Tupai'a's chart and said, okay, well, these island names belong to islands, but they're all in the wrong place. And furthermore, looking at Gladwin's book, what would happen if basically we looked at one moment in time, as near as we can figure, when Tupaia was asked by Cook, can you just show me on a map where these things are? And then apply the effects of wind and currents, and then have a computer sort of move the islands where they would be in an absolute reference system if that were the case. And all the islands moved to pretty much close spots where you see them on the map right now. And no one had done that. And the anthropologist's name was Ward, and he used the Cray computer UCSD to do that. So it was a pretty phenomenal thing, and a validation that these people actually kind of knew what they were doing. Well, David Lewis, who was a Kiwi medical doctor, was inspired by this kind of stuff. And he was a long-distance sailor anyway, had participated in transatlantic races and things like that. And he decided he would try on his own, without any anthropological training, to document the navigational techniques of these Pacific Islanders. As a sailor, he might be able to do a better job of that than a regular trained anthropologist. So he had a series of boats, but he traveled around throughout Polynesia, and mostly Micronesia, actually, where he was in contact with a number of these navigators, and sailed with them and sailed in their canoes, and then published that in a book called We the Navigators, and it became something on the order of a bestseller. And it became a source of pride of all of these island peoples who basically they'd lost their language in many cases. They had had their islands taken over by people from elsewhere. They often were the second-class citizens in their own islands. They had lost property. They were living in a world that had an alien set of values to the ones they were brought up with. And then suddenly, here was this guy saying, no, your ancestors were these heroic voyagers, that they were the greatest navigators who ever lived, that they could sail thousands of miles across open ocean and hit a tiny target dead on with perfect accuracy, without writing, without instruments, without charts, without mathematics, without any of these things that Captain Cook and other Europeans since had. They were able to do that. People still didn't want to believe it until David Lewis began to document it. And so there were several techniques that he documented. One was this sort of idea of sailing to windward and managing risk by sailing in these quadrants and tacking within these triangles, and dramatically increases the odds of finding an island anywhere within those search patterns. They also had to figure out how you deal with the fact of relative motion. The canoe is in the middle of the ocean. It's sailing through the water following a course, but you don't really know how the water is moving. There'd be no external way to detect how that is taking place, absent something like celestial navigation. And yet they could do that. So how did they do it? How were they able to cope with relative motion? Well, evidently, there is a human ability, if it's nurtured at an early age and it's done with a fantastic amount of study and dedication, that humans do have a homing instinct. And what Lewis and others discovered, that these navigators, when they started as young kids, they were trained to understand and internalize an internal compass. And it was based on the stars that surrounded them. Not just stars, because we know the stars move, but the stars would follow a pathway through the sky. So for instance, if you look at Orion, you'll see that Orion's belt, the 3 stars in his belt, come up at the same place all the time. Those paths always mark the same spot in the horizon. And Micronesians, or at least the ones that Lewis studied with, called those Avinga, or star paths. So they would come up at the same spot, and you could develop a compass from that and steer by them. More than that, though, that those stars, certain stars against the background, that even if you would basically know where a home island was, and if you had this whole cluster of stars you had cold, and you knew where your home island was, no matter where you were, to an accuracy within half a degree or so, you could always imagine a line between your canoe and that island intersecting one of the background stars. And that those series of radial lines along the course of a voyage would determine its length and how that voyage was segmented. It was a system called the ETAC system, and it divided the world up not into latitude and longitude, but into these series of segments formed of the canoe going along this course, maybe tacking along this course, and imagining or holding in your head the line between the canoe, the reference island, which is far over the horizon, hundreds of miles away, and the stars in the background. And this capability will exist for people that are trained in it, that it never goes away no matter how old they are. You can also use stars at their zenith, right, when they're at their height, just like, you know, the GP of the sun is right underneath. Right when the star's at zenith, that spot underneath might be one of the islands you're going to. So we did the thing about giving you the Z in of a location on the Earth that was under the sun, didn't we? And how to use a great circle, how applying that Z in, given the latitude and longitude of that location, and translating that into GHA declination would give you a great circle route. This isn't that much different than that, as you would catch the star at zenith and you would know what was right underneath it. So for instance, the famous voyaging canoe Hokulea is the star over Hawaii, okay, which I believe is Sirius, if I'm not mistaken. It's Arcturus, okay, Arcturus. And then Hikianialia is another star, which I believe is over Tahiti. Spike, okay. So in any case, they all had names, and they all had their reference islands right underneath them. They also were able to read patterns on the ocean. They were reading wave trains and so forth. As it turns out, as the wind generates a series of waves, and those waves encounter landforms, you have the same influences that influence all waves, refraction and diffraction. And if you're sensitive to how those wave trains interact, you can determine the distance and the direction to land based upon the wave train. You can also determine direction, so that when you can see the stars and steer by the stars at night, that wave train is probably going to persist over several hours during daytime. You start to steer by the waves at night, you continue on through the day, you pick the stars up at night again. So when you see, the Polynesians didn't do this, but you'll see Micronesia stick charts. We have one down in the exhibit. There's a nice one at the Valley High. Those things weren't charts showing the positions of actual islands. They were diagrams showing the way in which wave trains bent, diffracted, and refracted around islands and chains of islands. Okay, so they were transdictive devices. I liken them to models of molecules, right? If you see a model of the H2O, you're not looking at a molecule of H2O, you're looking at what all molecules of H2O look like. And so these were used as teaching aids to model the behavior of the surface of the ocean. They also were able to use what was available out there as signs to determine land from far away. So I took all of these pictures. The upper one was Tahiti. You notice the cloud formations that rise over the island. That's caused by heat rising up and the water vapor condensing into clouds. And likewise, you see Moorea, the same thing. You can see how the shape of the cloud mirrors the shape of the island. You can actually tell which island it is. The other thing, it's hard to see in this picture, but the underside of that cloud is greenish brown. Okay, it's reflecting the color of the actual island, and these are high islands. The lowermost island, Fakarava, which you can barely see, if you look at the clouds underneath, they're greenish blue, so it's reflecting the colors of the lagoon. And you can see this from, these pictures were all taken from some distance away and using the clouds. You can also, the patterns and the flights of birds, for instance. So for instance, terns and noddies will take off in the morning, they'll fly 20 miles out someplace, they'll start fishing around and hunting, and they'll fly straight back to their nesting or roosting area at the end of the day. Boobies and frigate birds do the same thing, but they're much longer range, 50 to 75 miles. So by all these means, you can take what is a tiny speck of an island and you can expand the target so it's much larger. And in addition to that, islands often don't come as little individual things by themselves. It seems that way, but when you expand the target, they become big sort of regions, right? In which anywhere in that region, you can see the signs of land. So for instance, it was pretty easy for the Vikings to cross the North Atlantic because they're headed for Greenland, which is pretty big. And when they were headed back, they're headed for Europe, which is pretty big. Well, an individual island might be small, but when you expand its apparent diameter out many times, and you combine it with the apparent diameters of all the other nearby islands, you're creating these blocks of water in which you strike that block, you can then go from there to the specific island that you want to go to. Well, all of these techniques were really exciting to people that wanted to sort of document that, and those efforts to document it go back a long way. Thor Heyerdahl's Kon-Tiki expedition, which went off on the wrong track because he thought that the Polynesians had come from Chile, was in 1947, but that stimulated this whole heroic period of experimental archaeology, building ships that ancient peoples might have used to prove they might have gone on the route you think they might have gone on. And this started with Chinese junks by a guy named Eric de Bishop, and actually in the 30s, and then the hybrid multi-hulls, Ka'imi Aloha and Ka'imi Wakea in 1939, and then more rafts, each one named Tahiti Nui in the 50s and late 50s, trying to sort of copy the Thor Heyerdahl's thing. But then the Polynesian Voyaging Society was founded by the archaeologist, or anthropologist Ben Finney, who's since passed away, Tommy Holmes, who's also passed away, and Herb Connie. I think all these guys have passed away now. Herb Connie was an artist. And they thought, well, if we could build a canoes and start sailing them around, we could build a canoe and sail between the islands, we might be able to recreate one of these heroic voyages. And so they thought, well, the American bicentennial is coming, all these tall ships are coming to the East Coast and everything else. We got our own version of that. And so this started back in the late 60s and early 70s, and their first canoe was this one, Nalehia, and it was successful sailing around Inner Island. And so then they decided, well, let's just build a voyaging canoe. It was designed by Herb Connie, and they began to sail between islands and got the notion, well, let's just sail this thing from Hawaii to Tahiti and back. And The problem was there was no Hawaiian navigators and there were no Tahitian navigators. So they obtained the approval and the participation of a famous navigator from, I think, Satawal named Maupialug, who sailed Hokulea to Tahiti, or he agreed to sail them, and he had to study the stars for a part of the world he was never in before, so it was quite a challenge. Concurrently with that, a young man named Noah Thompson, who didn't have the opportunity to apprentice with a traditional navigator, started hanging out at the planetarium at the University of Hawaii at the Bishop Museum and taught himself all on his own the star paths to many of these islands. And then he got involved with the Polynesian Voyaging Society and ultimately became its director and became one of its foremost navigators and foremost leaders. Ultimately, when Hokulea got to Tahiti, there was a huge outpouring there to welcome the vessel, and it was a validation, finally, after all these years, that these people that had been so dismissively considered by Europeans for not being able to do what they obviously were able to do because they didn't have things like instruments and mathematics and metallurgy and written languages and things like that. That basically they were capable of what is probably one of the most spectacular examples of intellectual achievement in all of human history, and that is the population and colonization of virtually every inhabitable speck of the Pacific Ocean more than 1,000 years ago. So that has since become, those canoes have since become an instrument of cultural revival. Every island group has its canoes. They get together and sail together. Sometimes they have crossed the Pacific. And of course we were fortunate to have Hokulea sailing with us the last time the Star of India sailed, and it was particularly poignant because the Star of India is the last ship sailing which once flew the flag of the Hawaiian monarchy. So quite a long course to run. And with that, we're done, guys. Thank you very much.